In this video, we're going to look at a traditional way of doing repeated measures analysis of variance. This model adjusts for the fact that the observations are not independent. So, for example, in our data set with the ortho-K lenses, we collected data over years, baseline 1, 2, 3, 4, 5 years for axial length. Now, in our analysis of covariance, we adjusted for axial length and looked at the difference between lenses at 5 years. In this video, we're looking at the growth of axial length over time. And so we have a time factor, a lens factor, and a time by lens factor. Now, we're going to go into Analyze General Linear Models, and we're going to choose Repeated Measures, because we're repeating the measurement on each subject, or each eye in this case, over time. And so we're going to, the first thing it asks the within factor name, and we're just going to call this time. And the number of levels, and the number of levels are 1, 2, 3, 4, 5, 6 levels. We add that, and we go to the next step by hitting define. Now it wants us to tell us what are those variables. So we're just going to highlight AL 0 to 5. We're going to click over here. We fill in all those spaces where those question marks are. Next, we add our between subjects factors. And this time, we're just going to look at lens type. So we have spherical ortho-K lenses and aspherical ortho-K lenses. We don't need a covariate in this case because we've already, we don't need the baseline covariate because we're adjusting for the differences between subjects by using this repeated measures over all these axial lengths. Our model defaults to the full factorial. We can look at options, and it will give us these. Now, it compares main effects. Unfortunately, it doesn't give us differences at individual times, but we're going to do the LSD. We can add our parameter estimates. And there's different things that we can look at: the estimated effect size observed, various matrices, homogeneity of variance, so forth. All right, so what do we get? This labels our dependent variables, shows us we've done what we wanted to. The lens type, the number, and the number of eyes, and with the spherical lens, and the number of eyes with the aspheric. Then it does this thing called a multivariate test. And what this is a test where the it's looking at the factor time, and it has it just combines it over all of the measures and gives us a value. We usually don't pay too much attention to this particular output. Now, Mauchly's test of sphericity. So the idea is that the observations for each year, the assumption of the analysis of variance is that they're independent. Well, this is a test of that, whether or not they are independent. If it's rejected, it says they're not. And so what that means is axial length at year 0 is correlated with year 1, year 2, year 3, year 4, and so forth. And when that's correlated, what we have to do is adjust for that lack of independence. When we come down here, we see the time factor, and sphericity assumed means that all the things are independent, and it computes an f-test and looks at the values there. Then there are corrections that can be made for lack of sphericity. And it doesn't really, the f-test hasn't really changed on either of these, mostly because we only have two groups. But there are a couple of different adjustments, the greenhouse geyser, the Hunfeld. And this is the absolute, things were really bad, you would use this one. But really you choose either the greenhouse geyser or the other. And again, there's only two groups, so it doesn't really affect the outcome in this case. And these are contrasts, so you can determine if the linear relation, or if time was linear related, if there was a little curve in it, if there were two curves in it, if there are four curves in it, and so forth. So those are different contrasts that can test. Here we test the lens type, and we see that it is significant. Then it gives us our parameter estimates, and it does it for each variable separately. Here are our marginal means, and again, this is collapsed over year. The difference between the two, as you can see, the aspheric lens is shorter length. It's a significant difference. Time, you can see that now it just numbers things 1, 2, 3, 4, 5, 6. This is actually here 0, 1, 2, 3, 4, 5, the way we've labeled them in our database. But you can see how the eye grows, 24.5 millimeters, 0.7, 0.8, and so forth. And this collapses across both lens types. And then it looks, and you can see that all the years collapsing across lens types are significant for each year. And this is really the table that you would plot. You would copy this, put it into Excel, create a graph, and show the growth. In fact, let's do that real quick. Copy, go to Excel, paste, I like the second one. Then we can replace these numbers with our years. Highlight the first set. Insert a scatter. We could do a scatter, we could do a bar. We can do anything. We're going to do one to connect the dots because it's line, it's kind of continuous. Now we're going to add another line. First we're going to call this spherical ortho K lens. And we're going to add a line, call it aspheric ortho K lens. Give it the X values. I wasn't too good to myself by covering up the values. It's right there, right there. And we can see that well, let's add a chart element, a legend. I'll put it on the bottom, get it out of the way. So this is the growth over years of our spherical lens. This is the growth over years of our aspheric lens. You can see this one has starts to slow down its growth. This one is pretty much linear, kind of flattish, and so forth. So that's analysis of variance with repeated measures. One final note. Notice that the repeated measures are in a horizontal fashion. The data goes this way. If you will recall, on our longitudinal vision data, we had a nit years and it went in this direction. We're going to need the vertical direction for the next type of repeated measures we look at using maximum likelihood methods. But this one requires it to go this way. There can be no missing data. Any year that's missing a value, the entire subject is dropped.